My name is Michiel Heinz, and I'm going to show you now how to carry out the damage calculation in this specific problem. So let's go up into the problem and let's see what we have. The question now is, if the stress spectrum refers to a block loading applied to the joint over 8 years, what estimated fatigue life would you make for the welded joint for a probability of failure of 5%? That is probability of survival of 95%. Now let's just copy this table down, because then I don't need to have a page up and down, and we want to do damage calculation on that. We've already determined the partial factor for fatigue. We did the temperature factor, we did the size factor, we did the detail category. We know it is a 90. We know the thickness effect, the point of crack initiation. Now, all the question that I'm answering here, where I did the SN curve, of course, let's number our questions quickly. Is question 6. I'm busy with question 6. So I want to, let's do this. This was question 1. And remember, it's always good practice to number your questions. This was question 2. And question 2 discussed the other influencing factors to take into account. Let's look at 3 and 4. What was 3 and 4? Detail category and what value must it take into account for thickness. Let's look at 3 and 4. The detail category, yes, this was question 3. And question 4. Question 4 was a thickness effect. Question 5 was where we looked at the point of crack initiation. And then question 6 is the damage and life calculation. Right, control UB. Now, and the first thing that we've done here is we've defined the SN curve, and what we're going to do now is perform the damage calculation. Now, I'm just going to paste the table here, and then I'm going to make a new table in Excel to demonstrate the calculation process for you. So here I'm going to say damage and life calculation. Right, control B, and let's highlight it with yellow so that we know where it is. Right. Alt AC, I'm just going to do that in the center, and I'm going to insert here a little object called worksheet, just an Excel worksheet that I'm going to install here. I'm going to repeat these values that we have there. So what we had is, in the first place, we had the detail category. Detail category for the specimen, and the detail category was given as, if I remember, as 90. Then we had the partial factor for fatigue, and that was 1.35. Then we had the thickness. Let's say thickness modification factor, and that was 1.0 in this case. We had the temperature, and that was 0.9, if you remember correctly. And now we can calculate the characteristic, the delta sigma C modified, and let's call it the characteristic strength of the modified curve, right? And let's make this column bigger, and we know that that was delta sigma C, and that was equal to, if we remember correctly, it was 90 divided by the gamma MF, the partial factor for fatigue, multiplied by thickness, multiplied by temperature. So we had 60 MPa. Then we must remember that 60 MPa is now called the delta sigma C modified, right? Let's see if we can insert that there. So it's a delta sigma C, delta sigma, close this, C modified that we have, and we want to put this as subscript. So let's format that cells and just say it's subscript. So there's our delta sigma C modified. Then what we have is the endurance NC, right? And the endurance NC, that is at the characteristic strength. And what do we know at the characteristic strength? If we look at the characteristic strength, that is equal to 2 million cycles. So it's 2 into the 6 cycles, right? And it seems as if it needs a little bit of space here, so it's 2 million cycles. The next factor that we need is the endurance at cutoff at the constant amplitude fatigue limit. And the endurance at the constant amplitude fatigue limit, the endurance at that point is equal to 5 million cycles, right? And then we need the endurance at the cutoff limit, and the endurance at the cutoff limit, sorry, not that one, I'll be, is equal to 100 million cycles. So there we have these values, and now we can easily calculate from this. Let's calculate it from this side so that we don't make the table too long. So now we can calculate for this, we can calculate delta sigma D. So let's insert that symbol there. We can calculate delta sigma. The first one that we need to calculate is D, right? And let's do this. And Control C, and then we can calculate the cutoff limit, right? There we calculate the cutoff limit, and then of course we need two characteristics of the SN curve. We need M1 and we need M2, okay? And M1 is equal to 3, and we know M2, the second part of the SN curve, is equal to 5. Right, so here we can calculate now delta sigma D. What do we know it is? It's equal to delta sigma C modified, right? And there shouldn't be a bracket there. There shouldn't be a bracket there. Multiplied by the ratio of NC, because we use delta sigma C as reference, divided by ND, right, to the power 1 over M1. Of course, we are on a slope of 3 in that regime. So that is 44.2084 MPa. That means if there are no stress ranges exceeding that constant amplitude fatigue limit, we will have infinite life. Delta sigma L now is equal to delta sigma D multiplied by ND, because you used delta sigma D as reference. That's how the SN curve works, divided by NL. And in this case, the slope is equal to M2 equal to 5. So that's what we have. Let's just present this a little bit better, because the values here are simply too much like that. Control C, Control V. And now we can model and calculate damage for our SN curve. Let's just move this a little bit upwards so that I can have more space here. And let's move this a little bit downwards so that I can have more space here. And I presume we will need a new page, so let's move to the next page. Right, now we can start to do damage calculations. And in our damage calculation, we're going to model the SN curve. That's basically what we're going to do. And I'm going to add here a few lines, and let's see where we are now. Right, so what do we have? What we're given to us is the maximum stress. In this case, they gave us sigma max, and I'm going to insert the symbol for that. I'm going to say they've given us sigma max, a maximum value of the sigma, I assume. And I'm not sure where they got it, but they say that's a maximum value for the signal. And then they gave us a minimum value for the signal. Let's call that one min. And they are both in MPa. We always put the units in our equations. We must have them there. So let's assume they are in MPa. Right. And then they gave us values 200 and 100, 50 and minus 75, 40 and 0. Now what we can calculate from this, let's just put these in the middle so that it looks a little bit better. What we can calculate from this now is the stress range. And the stress range in this case is the delta sigma r. So I'm just going to insert that like that as a symbol. I'm going to insert that as a symbol like that. So we want to calculate now delta sigma r, the stress range that was applied in this case, and that is delta sigma r. Right, and that's also in MPa. It will be the same units as these, and this will simply be equal to the maximum minus the minimum of the signals, and that's where we have in this case. Now I want to make a comment here at this point in time to clarify a few things. As you can see, these stress ranges contain one stress range, as a matter of fact, that exceeds the constant amplitude fatigue limit that we had in the table above. That exceeds the constant amplitude fatigue limit of 44.2 MPa. Right? So we do need to do damage calculations in this case. Now the number of cycles that they gave us is called Ni. That's just the small number of cycles, the small Ni. That's the number of cycles that we got from the information that were given to us. I'm sorry, this word is heavily frustrating. And they gave us, in terms of that, they gave us the following values. Right, I just want to put that little I at the bottom. Right, they gave us 100,000 cycles, they gave us 50,000 cycles, and they gave us 1 million cycles. And I just want to make sure my numbering format is such that I don't miss anything here. So let's make this number 0 and use that 1,000 separator. And now I can quickly see if I maybe didn't type in any values wrongly. Right, so that's what we have for Ni. This is the information that was given to us. And now what I'm going to calculate is the endurance, capital NR, and as we know, we calculate NR from the SN curve, the applicable SN curve that we have above. Right, and now to do that we say if, we do an if function. We say if the applied stress range is larger or equal to the constant amplitude fatigue limit. What do I have then? Then I have NR equal to delta sigma C. We can take delta sigma C or we can take delta sigma D, doesn't matter. Delta sigma C modified divided by delta, that and there we are at a slope of 3, and we must multiply that by NC because we used that one as a reference. Right? And now we need to dollar a few things. This should be dollared. B5 should be dollared, and E3 should be dollared, and B6 should be dollared. Now we ask the next question. If that's not the case, we ask if this value is smaller than the cutoff limit. Take the cutoff limit, right? And if it's smaller than the cutoff limit, then the answer is infinity. And we just type it like that. So it must give us a value of infinity there. And again, we need to dollar this because it shouldn't run down. And then we carry on. And if that condition is not true, then we're left with the section between the cutoff limit and the constant amplitude fatigue limit. And here we have delta sigma D divided by delta sigma R to the power, and now we are on a slope of 5, and we use delta sigma D as reference, so we need ND as reference, and let's dollar a few things there. E1 is a value that's not moving, C2 is the stress, C12, and B7 is number of cycles. That closes that if statement, and that closes that if statement, and we see that we might have a problem here, and it's got a problem with, it wants it to be written like that, and there we have it. And you can test this now with a simple calculation. 100 MPa is larger than 60 MPa, so we expect a number of cycles that are less than 2 million, must be. And what I always do to verify the accuracy of my answer, we know this is 100. Let's put in 60 in there. If I put 60 in there, the answer must be 2 million cycles. So let's make this a little bit bigger. Right, so we know we calculate it correctly. And if I put in the constant amplitude fatigue limit, let's put in 44, then I should get about 5 million cycles. All right, now let's put the original equation back. We know that we've calculated. And then, of course, another test. If we have 20, we should have infinity. 24 should give us approximately 24.4 should give us approximately 100,000 cycles, because that's close to the cutoff limit. And as we see, we're modeling the SN curve correctly, and we can proceed. Let's copy this down now to the bottom two parts, and there we have the endurances at the applied stress ranges. And now I can calculate the damage for each and every one of these conditions, and the damage here is simply equal to the number of applied cycles in the block divided by the endurance, and I do this for all of these, right? And the total damage is then, of course, let's line this, is then simply equal to the sum of the above. That's the total damage. Now, that total damage, according to the information that were given to us, were done over a period. That's the period of the table that were given to us. The stress spectrum was 8 years. And then it means the fatigue life, in this case, will be equal to 8 years divided by the total damage. And as we can see there, it's approximately 13.8, and the unit is equal to what the unit is there, years. And that is how we perform the calculations. I'm just going to make the table look a little bit better. I'm going to put a line in here, because remember, this is coming on your website now as part of your class notes. So I'll just put in a few lines here to make this look good, right? And normally we give a little bit of shadow here. We make this bold face, and of course we fill the area with a little bit of oil, so that we get a little bit of a contrast there. And as you can see here, if the block was measured over 8 years, the fatigue life in this case will be 13.8 years. Now let's see if we can make the table look a little bit better, because as you can see, it's very big at the point in time. What I can do is I can we can maybe remove the characteristic strength modified and just use delta C mod, and then I can move this line to the left. I just want everything to fit in better. We can move that to the left. That looks fine. We cannot move that line. That line cannot move. That line cannot move. So there is our table, and let's put a line in there at the top so that we give a little bit of contrast, and the table stands out a little bit, and that is how we perform the damage calculations according to the Paul-Germainer rule on a weld fatigue detail. Now, if you have other detail categories or other areas that you need to check, all that you need to do is just do the appropriate checks. If you have other benefit factors that you need to take into consideration here, just do it. And this summarizes the whole process. So, based on the information provided to us, the fatigue life is 13.8 years. Now, if you look at the last question, the last question asks, what improvement in detail category is possible in this case with hammer pinning? If we hammer pin this weld, remember the damage that we calculated here was the damage for crack initiation at the weld toe for the transversely loaded weld. So that means we can improve by hammer pinning. So if I go back to the notes that were given to you, and we look, we find the area over pinning and the effect of pinning. And here we are at pinning. So here you can see, of course, maximum possible fat after improvement is 112. Fat classes for use with nominal stress are joints improved by hammer pinning. Now remember, that's the fat, that's the detail category that you read off from the curve. So that means it's not, if you look at this example, the 60 that must be multiplied by the factor. It's the 90 that must be multiplied by the factor. So in this case, we can have improvement, and I will make the modification here. Let's say we have pinning, so I'll add a line here so that we can model the effect of pinning. And remember now, you will see where everything comes from. Let's insert here. Let's say pinning benefit, and of course it's 1.3 to 1.6. Let's go back to the notes so you can see. Let's assume it's mild still in this case, and it's 1.3. And please note, you cannot exceed 112. So if I go back to this one here, right? What is 1.3 times 90? 90 times 1.3 is 117, right? So if we want to model the effect of pinning, we need to look at the fatigue factor right at the top, and it means that the maximum value for the detail category in that case will be 112, and that's what you need to model. So you can increase this to 112 to model the effect of pinning in this case. So if you pin this well, let's make this number look better. So if you pin this well, you can see here the life will increase to 28.8 years. Right. Okay, so that's the effect of pinning. I'm just going to remove it in this case and just take it back to 90 so that you don't get confused. Or you know what I will do is, let's copy this table. Let's copy this table. And I'm going to make another one here, Alt AC. So this is question, I think it's question 7. Question 7. Now, to consider the effect of pinning, I must first look at that 90 because it's the fatigue class that can move up and down. Now, in this case, it will be equal to the maximum. So the value that we will have here is equal to the minimum of 90 times 1.3 and 112. And in that case, you will see it works out at 112, and everything else stays the same. And you can see if you pin, you increase the life to 28.8 years. So we can have a substantial benefit. After the period, of course. So there we know the effect of all these, and we can model the SME.